This section is simply the science of measurement. Why do we measure anything in the first place? Okay? To understand the system we're interested in. It's the object of interest, so we measure it. How do we measure that? Well, it's important that you understand the significance of a measurement. And it's real easy to remember these, and I put it together like this. You'll remember MALT. Measurements provide meaning to object of interest. Everything's going to be about the object of interest, obviously. Measurements answer questions. About the object of interest, of what you're looking at. They limit applications to the object of interest. They define limits, actually. Limits about or applications. And T, and is a tool for describing object of interest. And so if you will appreciate the concept of measuring things in that context, it's easy to remember. It is all revolving around that object of interest. Why are you measuring anything? To get that information or signals or understand the language of the object you're studying. Okay? Meaningful measurements. Must do three things. Define quantity being measured, establish a standard associated with the object, and three, compare measurements, measurement data from object to the standard. Simply define, standardize, and compare. Length. All right, everybody knows what a length is. Standardize, 1 foot. Everybody got an idea. How does that compare to a mile? Bigger or smaller? Or an inch? Bigger or smaller? So that's what I'm talking about. Once you establish what you're talking about, length of weight or time or lumens or brightness, sound, volume, on and on. These are called fundamental quantities, length, weight, time. In each case, you want to establish a standard that you can compare other measurements to. And so that's in essence where we are in our notations right now. Because in any measurement, it contains 2 things that conform to this idea. Because it's a meaningful measurement. Measurements must have meaning. And they require 2 items for any measurement. All measurements scientific primarily should contain a number, a unit, and an uncertainty factor. And so that's where we are. My job now is to teach you about numbers, uncertainty, and manipulations of units. Much of this you are experienced with. Anyway, enjoy the review. For those that are not so well grounded in this, please pay close attention because this is something we'll be using throughout the course. So our next topic is goes from essentially is the content of measurements, in which I will cover uncertainty, significant figures, exponentials, notations, and mathematical equations, and then we'll go to units and some conversions, equivalent relationships. So, what are significant figures? These are all figures known with certainty plus 1 uncertain digits. Many of you have already experienced this kind of issue when dealing with, say, length measurements. Let me see if I can get an example. Okay, so here's a line that we want to measure. And so we take a ruler and we place it up here next to the line, and we say, well, let's see. Now, that measurement is, I'm going to go with metric. That measurement is 70.0, almost 70.1, somewhere in there. Now, we can zoom this and show you a little more accuracy in this. Right here. It's not real clear, so you can see in here where it kind of splits some number lines in here, back in here, back over here. Man, it's kind of hard to point, but that's 7 centimeters and 7.1, I guess 5. So if we identify that as 7.15 centimeters, these are the digits that are known with certainty. And of course, that last one is an uncertain digit. So that's the nature of what we're talking about. And of course, that applies to measurements that kind of, as we say, split hairs, even on balances and weighing mass and so forth like that. If you were using a balance beam or something of that nature, move that down a little bit, as you can see it. Anyway, we'd be making measurements that contain this. Now, the decimal placement in here is what we would call the accuracy of the instrument. If you were measuring these lengths, this is accurate to actually 0.1, but because the last digit is uncertain. So when we defining the accuracy of the measuring equipment, let me get back to so let's see. Is the known with, let me put it down here, depends upon, that's what that means, depends upon the known, digits known with certainty. And then the uncertain digit does not define the accuracy of the measuring tool. So we can say, in general, this instrument or this ruler is accurate to 0.1 millimeter, or 1 centimeter. We're measuring in centimeters, aren't we? Yeah. And 0.1 centimeter, because that is the limit of the accuracy of the tool we're using. And of course that is also applied to weight devices and time devices or whatever you're using to measure the data stream that you're trying to collect as such. In your outline, you will find the rules for significant figures are posted at the bottom of the page 1 outline if you have it available. If you do not, you can just go online and get it at your leisure if you have any. And it kind of itemizes things that refer to how to round numbers off and express numbers in the appropriate number of significant figures. Now, these are revolving around, as you can see, and you can read as easily as I can, all non-zero digits are sig figs, and so this shows you 1, 2, 3, 4, 5 digits are significant. They have things called enclosed zeros. Those are sig figs. Leading zeros, like these, are not significant figures. Okay? That is, if you're counting digits from left to right, the first sig fig number would be the 8 in here. Trailing zeros are significant figures if they have a decimal in them, because these last 2 digits in whatever is represented is like the accuracy representation of the instrument that you're collecting the data. So a trailing zero usually has a decimal, but you have some trailing zero in there that do not have a decimal, and they are not significant in that this number is the average distance from the Earth to the Sun. Okay, 96 million miles, but it only contains 2 significant figures. Now, there is what you have just given you is just a system of black and white rules, and it's difficult to remember one of those rules, much less all 6 or 7 of them. But there's a system that's used that I want to show you the video on, in which the determination of the digits depends on where you count, which side of the number you count from. For example, this one, if you have a decimal in the number, you always start left to right if you have decimal present. But if you do not have a decimal, you count right to left. And when you count, you go through the zeros, and when you hit the first non-zero digit, that's when you start counting your significant figures, like that. Here it has a decimal, so you count all of these as your significant figures. But this one, it does not have a decimal, so you go right to left, and you only have 2 sig figs. Now, not sig figs doesn't mean they're eliminated. I'm sure you can appreciate that. But these are there for magnitude. But in terms of the significance of only the first 2 digits would have any reasonable measurements. So what I'm going to do now is show you that video on the significant figures. So enjoy. There we go. Not very clear, is it? Let's see if I can get a little better. Okay. So how do we count the first one? Well, here's the decimal. Looks like everybody's got decimals. And here's one that's no decimal, and this one's no decimal. So if we have decimals, we're left to right on all these. So if you would fill in your blanks real quickly, I think you can do it in a matter of a second or two for these, and we'll check these. So here we have 1, 2, 3, 4, 5 is what I see, and we have 6 for that one. We have 4 for that one, and this is not counted. The 6, 7, and 8 are significant, so it's a 3. So is everybody comfortable with this idea? So it's pretty straight, but very significant and important that you have a grasp of kind of how to count these out. Another decimal, so that looks like a 4 there. Here is left to right the not significant zeros, so this one would be 3, and here these are after the decimal, so left to right would be 5, and this only has 1 because you go left to right until you hit a non-zero digit, and then you start your count from there. Is everybody okay on that one? Okay, good. No decimal in this one, so the count would start from right to left in this case, go through all the zeros, and this would have only 1 significant figure. Here we have a decimal, so we'd need to count left to right in that one, and we see 1, 2, 3, 4, 5, 6 significant figures in that number. Here left to right, but we have to take into account all 4 zeros in this case, as trailing zeros are significant if there is a decimal, and so that is 5 significant figures. Here it is no decimal, but in counting, we find a non-zero digit in the first position right here, and then we have to count the zeros as well. 0, 1, 2, 3, 4, 5, 6 significant figures in that. So if you have any questions about that, certainly check mark it and let me know, and we'll certainly go back. You have access to the video. You can review it at your if you feel like you need to. Now, the rest of this is for the rest of it. These are math operations and significant figures. This one right here is going to be my demo for right now for math operations. So, all right. So here is addition and subtraction in sig figs. Let's see. There we go. Like that. There we go. Now, we have what we call calculator answers, and we have rounded to the appropriate answer based on counting of significant figures. So, I've got to get this over here. Okay, so the calculator answer would be 7, 3, no, that's 7, yes, 6. I'm trying to line these up. 6, 6, 12, 13. 6, 7, 8, 9, 10, 11, 12, 5, 6, 7, 8, 9, 10, 2, 3, 4, 5, 6, 7, 8, 9, and 3 is 6, 169, 0237. Now, the way the rules read is you round it to the number in the computation having the least number of significant digits to the right of the decimal. Okay? So in this computation, there's only one position to the right of the decimal right there. And so what you need to do is identify that position as your last position in your appropriate answer right here. So this should be rounded to 169.0 in that computation. So as you see in the other calculations, you will do the same thing. So if you would take a second and work these two, and you notice the digits having the least number of significant figures to the right of the decimal, and then you'd line those up to match the position. There. So if you can see them. Okay, so in the first one we did on the screen, but it came out 169.0, and the second one should have come out 582.8, and the last one 2026.8, based upon the positioning of the number of digits to the right of the decimal. Everybody okay on this? Any questions? It's very straightforward, and there's no tricks in that. Now, if there are no questions, we'll move on to appropriate significant figures in multiplication and division. Okay, now pause. This is your calculator answer, and that comes out of punching into, of course, the calculator. But we need to round it to the computational data point that's in the calculation that has the least number of significant figures. Now, that would mean, since this has a decimal in it, we count left to right to identify two significant figures, in the same way here as a decimal would go left to right, and so that would be 90. And if you wish to put the decimal in there, that's fine too. But some people don't, but they identify the sig fig by putting a hash mark over the top of it like that. So that's an appropriate rounded to two sig figs in that computation. So going to another one, applies in this problem, 45.76 times 0.25 equals 11.44. But as we look at the computation, which of these has the least number of sig figs? Well, obviously this one only has two significant figures counting left to right, so this would need to be rounded to 11, which is two sig figs. So that's in essence the nature of multiplication. Multiplication. Well, the same way is true for division. If you look over at problem F on the right side, you see 1.678 divided by 0.42. And so the calculator answer, so it kind of strings things out and shows quite a bunch of digits. And but according to the rule, we want to round this to a position that has the least number of significant figures in the computation, and that in essence would be, in this case, two significant figures, as shown in this one. So, find that. Okay, so this would be rounded. Okay, we use the rule of 5 in here. I haven't mentioned that. If the last digit is 5 or greater, then you round it up to the next whole number. So since we're rounding to two significant figure positions, this is 2 sig figs here. Then we want this number rounded to 2 sig figs, but the last number that we are going to drop is greater than 5, so we have to round up like that. And so this in essence would take that 9 into one higher, which is 4.0, and we have to retain the 0 and the 4 to qualify as two significant figures, because with a decimal we count left to right, and this would represent 2 sig figs in that final answer. So that would be the appropriate computational number. Now, we don't have time to go through all of them and work the entire process, but I will give you the answers I got in this. So give me a second here. Okay, I'll try to zoom that portion up. A little smaller. There we go. There's a little better flavor to it. Right there. That's better. When we talk about scientific notation in measurement, the shortest answer is this concerns itself with powers of 10. And in that, a number can be converted to what we call an exponential notation as a function of powers of 10. So when we talk about powers of 10, they are in relationship to what are decimal fractions as power of 10. That would refer to 10 to the first power. Now you can go to sizes smaller than 10 or larger than 10. So if you go to smaller than 10, you're using a negative exponent. You're subtracting from this. This is 10 to the first power right here. So that means it's just a measurement of 10. And essentially means the decimal place is right there. And the larger than 10, you don't have to put the plus, but you would have a positive exponential notation onto the number to indicate that there's so many times the power of 10, whatever it is. Now, the way I do this is I start out with a number line. Just give yourself a little bit of room here, and we'll start in the middle here with say the value of 1 here, and that represents a power of 10 to the 0. So any value 10 to the 0 power is 1, and if we go up to 10 in itself, it'd be 10 to the first power. But if we go to 100, that is 10 times 10. It means we're multiplying twice the same number, 10 2 times, or 10 squared. And if we go to a number of 1,000, it's 10 times 10 times 10, and to the third power, 10 to the third. And we can go 10,000 if you wish, 10 times 10 times, and so forth. 10 to the fourth power. So it places the decimal next to the 1. And so if you start here and move the decimal, it's the number of places you move. But you count this first place as a 0. And then 1, 2, 3, 4. And so you have 4 positions. Now, if you go to a fractional consideration like 1/10, which is 0.1, like that, then you are subtracting a position. You're going from here to the left in your measurements, so that'd be 10 to the minus 1. If you get 1 over 100, that'll be 0.01, and that would be 2 places back to there. And that's 1 minus 1. You have to move 2 places to the right, and this would be 10 to the minus 2, like that. And maybe kind of confusing, if you're just getting into this, or if you have 1 over 1,000. And all this just means what it is. Move 3 places from the decimal place, that's 10 to the minus 3. And so that expresses it as a power of just 10. But the application of this is to express numbers in exponential notation, and refers to the number of positions you move relative to that number. Okay, when you're given a number as written, you assume the decimal place is in the position right here as given. Now, if it's a decimal fraction, 0.123, it has to be given. Now, sometimes the numbers without decimals will be just written like that. And so to convert these to exponential notations, it depends on how many places you have to move. And so that could be anywhere you want. You could move it to the position between the 2 and the 3, or you can move it to the position between 1 and 2, or you can move it outside there, or even add zeros and go. You have the choice depending on the circumstances of the problem and what you're doing. However, it is standardized if you place this number in a form that lists it as a number between 1 and 10. Okay? So listing it in between 1 and 10 is the standard form. Standard form would be 1.23. Same here, 1.23. Then you have times however many places you move. So in this case, we would move 2 places from right to left. So this number is 10 to the 1.23 times 10 squared. Now that's standard form. However, I'm not going to do it that way. However, this is equal to 2.3 times 10 to the first power. See where we just moved 1 position like that. They're identical numbers, but the one here, which is 1.23, is the standard form. Down here, the standard form is where did we start and end. We move 1 place to the right. It's a decimal fraction, and so we have to use negative positions in that case. So we move 1 place to the right. Well, this is equal to 2.3 times 10 to the, if I move 2 places, minus 2. The power of 10 is how many places you move from origin. You 0, 1, 2, 3, or however many. So that we could, and the circumstances dictated, have a 1, 2, 3 times 10 to the minus 3, or 1, 2, 3, 0 times 10 to the minus 4, and so forth. All of those are the same numbers in here, but only when this is called a coefficient, is between 1 and, 9.9999, whatever, between 1 and 10, is it in standard form? And when you look at problems in the textbook or in the literature, it's most likely going to be in standard form. But that doesn't mean that under certain circumstances you can't move it around, and we'll show you that in addition to subtraction especially. So that's the essence of this. Now, that's converting numbers to to exponential notations. You also will need to be able to convert numbers in exponential notation back to just digital form. If you have a 1.56 times 10 to the minus 2, what is that in just writing in digital or decimal fraction form? Well, it tells you got to move this 2 places to the left. And so you would typically put a 0 in front of a decimal, as convention would dictate, 0.0156. So this is the conversion back to the decimal form, or 128,001, and put that in exponential, wait a minute, excuse me, I'm sorry, I didn't want to go that far out, times 10 to the 4th power. Okay, being positive, that means, I'm sorry, I didn't put it there. You would need to move to the right by 4 places. And so that would be 12800, put your comma there, it'd be 12,800. So it's forming the exponential notation as well as taking the exponential notation and going back to the decimal number. If this is still confusing, there is a nice section in the appendix of Ebbing, I know, that gives you more examples, and of course you have the worksheet there that you can work through on exponential notations. Okay, now that's the converting issue from decimal to exponential. Now we need to look at the math operations. Okay, so if we're going to we'll start with multiplication and division. I'm just going to set up a problem in here. I'm going to find one somewhere. Yeah. If you are multiplying, the exponential values are algebraically added. So you want to algebraically add with the multiplication. And then if you are dividing exponential values, it's a subtraction. Okay, so let me set up a problem. 8.12 times 10 to the 4th power times 6.3 times 10 to the minus 2 power divided by 2.04 times 10 to the 2nd power, and 7.11 times 10 to the minus 4 power. Okay. Now, this is probably the only time I'll ever go through this like in this context and lay out everything, but it's strictly for academic purposes. Now, one way to approach this is to take the coefficient numbers. Of course, everything's in standard form, so I'll collect the coefficient numbers in one part of the calculation like this. And then a second part, put a times sign, and then put the exponential notations over here like this. I'm going to change that to a 3, okay? Let's change this one to a 3 so it won't cancel totally. Make that a minus 3. And that's the positive 3. Okay, and then 10 to the minus 4 right there. So you have individual calculations going on between the two. So it's 3.52692976. That's your calculator answer. Okay, and then shoot up. And then we compute this. Well, essentially, this is 10 to the 4 plus 4 plus a minus 2. You add those together, and the denominator the same way, plus 3 plus a minus 4. And like I say, this is the only time I go through this kind of detail. And so this one comes down to 4 minus 2 is, of course, a plus 2, and plus 3 minus 4 is 10 to the minus 1, like that. So, like that. And then for the division, we subtract algebraically plus 2 minus a minus 1. Minus times a minus is a plus, so that translates into a positive 3, and then we have 3.5269297.6, like that. Now, according to the rules, we round that number to the computational data with the least number of significant figures. So you see that this 6.3 in this computation is the least number, and it's 2 sig figs. So our final answer should be rounded to that position, and so it is 3.5 times 10 to the third is the final appropriate answer form. Now, there are many opportunities to make these conversions in the worksheet and practice the skill on it, and if you have problems with it, certainly get with me then, and I will make every effort to try to help you along in understanding that. Okay, now addition and subtraction is the next. The essence of this is when you add the coefficient numbers, the powers of 10 all have to be the same. Convert. And that's iffy or standard form. It depends on what you're required to have in the computation. So there's a double option here in that. So let's take 365.2, 1.871, 62.44. Like this. Okay, yeah, we can add that and get a computational number, and it's not a problem. But the idea is to express these in standard exponentials. That'd be 3.652 times 10 to the plus 2. This one is already in standard form, so we'll leave that 1.871. Actually, that's times 10 to the 0 if you want to put 1 in there like that. That goes to 1. And then 6.244 times 10 to the first power. Well, according to the rules, you cannot add these numbers down here because these are not in the same position for your exponential notation. So it's a matter of where do you want to express everything. Well, this is really the least number. So you got this one at 10 to the 0 position, so you need this one at 0, so you moved this one to plus 1, so to go to 0 you would have to move back this way, so that would be a 624.4 because that moves back to the right and subtracts off that positive 1 exponential notation. See, this is 6.224 if you move to the right, was right here. But if you want a 0, let's see, you would have to, only a 6 point, that's to the first power. Yeah, going back, it subtracts it to this side, so that's what that one is. And this one's times 10 to the 0, 1.871. You can tell we don't use this very much. And then this one also converting to the first power, just move it one place over here, and that's 36.52 times 10 to the, well, running off the screen, 36.52 times 10 to the first power. No, that's first power, 0 power, so it'd have to be 36 0. And that one is also times 10 to the 0. Now you can add them together. I know that's a mess, and I apologize for that. Let's come down here then. 36.52 times 10 to the 0, and then we have 1.871 times 10 to the 0, and then 624.4 times 10 to the 0. Now you can add that because all of these are in the same order of magnitude. And so that is, just to make this, okay, so that's just if we convert. Now you could have converted this number to a power of something else up here. So, but the main thing is that they all have to have the same power of 10. Let me finish this. And then 6.62791 times 10 to the second power if you move the decimal correctly. And then if you put it into the least number of significant figures, 4, 4, 4. So 1, 2, 3, 4. So this would be 6.628 times 10 squared would be your final answer. Okay, so making that correction here, I get this. So just rushing. But I wanted to get into the conversions, get out of this. Let me get that started, and then we'll pick up here. 6 and 1.